Hello, my name is Noah Stoffel. I'm a mechanical engineering student at San Francisco State University. I'm also a member of Dr. Azadi's Fall Engineering 415 Mechatronics course, where we learn how to assemble and program simple robotic devices. Today, I'll be talking to you about a self-balancing robot that uses a centrally mounted inertial wheel, an onboard IMU, and a complex PID loop to detect and counteract instability in the motorcycle. The self-balancing motorcycle project is one of 3 projects included in the second revision of the Engineering Arduino kit. In a previous video, I touched on another project from the Arduino Engineering kit, the image drawing robot. There, I explained how we can use MATLAB to form complex programs that can be directly uploaded to the Arduino controller. In that project, we loosely touched on making real-time changes to the code in MATLAB and watching them be executed by the robot. We will expand on that topic when discussing the real-time tuning of the PID controller. While you would expect a motorcycle to be able to drive and balance at the same time, we have decided to limit the scope of this video to just being able to balance in place, as the introduction of motion to the system adds a lot more complexity to our calculations. In order to create the self-balancing part of the motorcycle, we needed a few parts of the engineering kit. This includes the motorcycle frame itself, an Arduino Nano 33 IoT, a motor carrier board, a LiPo battery, a DC motor with rotary encoder, and an inertial wheel. Assembly instructions can be found on Arduino's website under My Courses after purchasing the kit. The Arduino Engineering Kit also comes with prefab MATLAB scripts that help users through initial setup and testing with Arduino devices. Although, as stated in my previous video, something to keep in mind is that the current version of the MATLAB to Arduino application does not support newer versions of the Arduino Nano firmware, so you have to downgrade to at least version 1.8 of the Arduino firmware. Here you can see the final Simulink file for the self-balancing part of the motorcycle. There are 2 subsystems that feed into one another in the loop. The subsystem on the right controls the output signal to the inertial flywheel motor, as well as the input signals from the onboard IMU, the rotary encoder, as well as the status of the battery voltage for the entire system. The subsystem on the left contains a number of subsystems inside itself as well, one of which is the subsystem that controls the pre-processing of the input signals before being sent to the PID controller subsystem for tuning. At the top of the page, we can see a yellow box that corresponds to a number of if statements that check whether the motorcycle should enable its balancing mode. We can also disable the self-balancing feature of this robot using the toggle switch on the top left. Inside the controller subsystem, we see our main 3 gains that we would use to alter the control of the responsiveness of the inertial wheel. In my case, these are the 3 values that allow my motorcycle to balance. However, these values may differ from person to person. We can monitor the results of our changes in real time using Simulink's Monitor and Tune feature. In most cases, the robot will not be perfectly balanced once it's built, and this could be due to a number of manufacturing errors, the presence of a programming cable, or any number of other reasons. But back in our sensor pre-processing subsystem, there is one more value to be aware of to correct for this. That is our balance bias term. We can monitor in real time which direction our motorcycle tends to favor most when falling over, and use this bias term to offset our calculations to accommodate for this natural imbalance. By varying these 4 values, we can find a response that allows for our robot to balance on the spot indefinitely, even accounting for slight shakes or perturbations in the robot itself or the surface it's resting on. I want to thank you all for watching. If you have any other questions regarding this project, you can email me here at my school email, or you can find me on my LinkedIn profile. Thank you. Have a great day.